Okay, we're going to solve the Bessel equation, and I've already got a start on it because this is all the stuff that we do every time. The Bessel equation is x squared y double prime plus xy prime plus quantity x squared minus p squared times y. P squared can really be any number, and when we find the indicial equation for this, r turns out to be equal to plus or minus p. And so we can't really tell what case the Bessel equation is going to produce until we know what p is, and p differs from problem to problem. We'll assume first that p doesn't differ by an integer, and that way we can treat it as a case 1. I went ahead and took the liberty of writing the three derivatives where r is equal to p. So now all we have to do is substitute and see what we end up with as a recursive relationship. Okay, we luck out a little bit because substituting this in produces almost all consistent indexes across the board. Here's what it's going to look like. Summation n equals 0 to infinity of this guy n plus p times n plus p minus 1 times an x to the n plus p, because the x squared takes care of the 2. The middle term is going to be summation n equals 0 to infinity of n plus p times an x to the n plus p, because the x takes care of the negative 1. The third one's where we run into some trouble. It's summation n equals 0 to infinity of an x to the n plus p plus 2, only because the x squared adds 2 to the base factor. And then the last term is going to be minus summation n equals 0 to infinity of an x to the n plus p. And we need the p squared coefficient, and that comes from this one right here, minus p squared. Okay, all that adds up to 0, and we do have to change one index. 3 of these summations have powers of n plus p, but one of them, this one right here, is n plus p plus 2. So I want to replace n with m, which is n plus 2. That's going to serve to remove the 2 here, and we'll just replace the m by an n. N is going to be replaced by m minus 2, so the new n's have to be minus 2 also. So that's going to be a n minus 2. And this series will have to start at 2, because there's no such thing as a minus 1 or a minus 2. Okay, now what we're going to do is rewrite the series in terms of its new exponent. The only problem is this one doesn't start till 2, but the other 3 start at 0. So what I want to do is basically break it into 2. Summation n equals 0 to infinity. I'm going to put all these parts together that all start at 0. So what that's going to do is make it n plus p minus 1, n plus p times n plus p minus 1. And then that is going to be plus n plus p, and then minus p squared, and all of that is all an x to the n plus p. And then the only other part of the series is this one, summation n equals 2 to infinity of an minus 2x to the n plus p equals 0. So now what we can do is generate the first 3 terms of this one. First thing I'm going to do, though, is I'm going to go in here and simplify this, because n plus p is here and here, so I can factor it out. And what's left behind is n plus p minus 1 plus 1. So that's n plus p squared minus p squared, just a lot easier to write. So let me put it in a different color. But that way when we are generating terms from this, what this really is n plus p quantity squared minus p squared. That's the entire thing in those parentheses. Okay, so let's generate the first few terms. So when n equals 0, what we're going to get is this guy times a0 equals 0. And this guy, when n equals 0, is just going to be p squared minus p squared. Well, that 0 all on its own times a0 equals 0. Well, by the zero product rule, that's nice. That means A0 does not have to be 0. It can be any other number because what's in here is already 0. Of course, we knew that would be the case because this is just the indicial equation, and we knew by picking r equals p that we'd be solving it. Okay, so that doesn't really give us useful information other than the fact that A naught is preserved. N equals 1. Again, this one's still not going to generate anything, so this will just generate A1. So again, with 1 here, it's going to be p plus 1 squared, p plus 1 squared minus p squared. And all of that times A1 is going to be equal to 0. Well, this then generates some problems. Remember, p is supposed to be general. The only limit we put on it right now is that the difference between plus and minus p shouldn't be an integer, but that's just a convenience so that we stay within case 1. It's not necessary, and yet you see that p plus 1 squared is p squared plus 2p plus 1 minus p squared. That means 2p plus 1. In order for A1 not to be 0, 2p plus 1 would have to be 0, which means p could only be negative 1/2. And p is supposed to be a general variable. We can't limit it like this. And what that tells me then is that A1 has to be equal to 0 in order to preserve p's generality so that it can represent all Bessel functions and not just this one. Well, that's good. That means actually that it's very likely that all the odd functions will be 0 because this is a recursive relationship that skips 2 orders. A naught is related to A2, A1 is related to A3. So if A1 being 0, I think all the odds are going to be 0 too. So that's good. That means we can just focus on the evens. So when n equals 2, we're going to get the whole recursive relationship. We're going to get p plus 2 squared minus p squared. And then that's times A2, and then that's plus A naught equals 0. And that gives me the recursive relationship, or at least the relationship between A2 and A naught. And what that tells me is that A2 is equal to negative A naught, and then that's divided by p plus 2 squared minus p squared. Let's work out what that is. That's p squared plus 4p plus 4 minus p squared. That's 4 times p plus 1. 4 times p plus 1. So that is A2 in terms of A1. Well, let's skip A3 because we know it's 0. All the odds are 0. Let's go to n equals 4 and see what we get. When n equals 4, it's 4 plus p, or p plus 4 quantity squared minus p squared. And then that's going to be A4 plus A2 equals 0. So that's going to tell me that A4 is equal to negative A2 divided by, this guy is going to be p squared plus 8p plus 16 minus p squared. That's going to be 8 times p plus 2. So it's 8, or let's say 4 times 2, times p plus 2. Okay, so it looks like there's always a 4 underneath, and then let's use this final substitution to say A4 is also then equal to A naught divided by 4 squared times 2 times p plus 2 times p plus 1. Okay, I think I'm ready to write the recursive relationship then. And I'm going to do it in terms of 2k because all of these are even. So it looks to me like A2k is equal to negative 1 to the k, because we get the back and forth negative positive, times A naught. And then that's all divided by 4 to the k. Yeah, because when k was 2, we squared 4. And then this is always going to bring in not just 2, but the next time it's going to be 3 and then 4. So this right here is k factorial. And then the last thing is this this multiplication of p plus 2 times p plus 1, that's only going to go up to p plus k because k was 2 and that was the highest one we had. So this is really going to be times p plus k, and then that'll be times p plus k minus 1, and it'll go all the way down to p plus 1, and that'll be the last product that's part of it. So that's a weird sort of factorial that goes from p plus k down to p plus 1. Okay, so that then gives us the series solution, which is y is equal to the summation n equals 0 to infinity. Once again, I'll call a naught just 1 for a moment. We're going to come in and replace it with another value in a bit. Negative 1 to the k. And then that's all x to the k. Oh, excuse me. It's k equals 0 to infinity. K equals 0 to infinity. Because here come the two k's. So we've got then 4 to the k, k factorial, and then this weird p plus k times p plus k minus 1 all the way down to p plus 1. Okay, and then I'd like to say that this is equal to the Bessel function for p, but it isn't quite there yet. And the reason why is we need a specific value. I'm going to put a naught back in there. We need a specific value for a naught to reduce this down to that. And that value for a naught, which will turn this into the Bessel function, is a naught needs to be equal to 1 over 2 to the p, and then the gamma function of p plus 1. Now that introduces the new idea of the gamma function. This p to the 2 to the p is just a constant. What I want to do is get rid of some of this stuff so I can get some room back. And what we want to do is examine what happens to this when we use this as the value for a naught. And again, a naught can be chosen because it's just a constant for the series. And this particular choice of it is actually going to have some great ramifications that make JP look a whole lot easier. So let's write this out again. Y is equal to the summation k equals 0 to infinity of negative 1 to the k, x to the k, and then all that's divided by 4 to the k, k factorial, and then this weird p plus k minus 1, all the way down to p plus 1. And then I'm going to write in what a naught is. So a naught is 1 over, so it's times 1 over 2 to the p, and then the gamma function of p plus 1. Okay. Now, first, let's talk a little bit about the gamma function. We're actually going to spend some time on this later this week and look at some of its properties. You can kind of think of the gamma function as a new way of describing a factorial. As a matter of fact, it can be used to prove that 0 factorial is really equal to 1, which I'm sure has bothered a lot of you for years and years. What we're going to use it for here is in simplifying the Bessel function, because one of the properties of the gamma function is this one, and that's that gamma of p plus 1 is equal to, one of the properties of the gamma function overall is that gamma of x plus 1 is always equal to x gamma of x. We're going to apply that here by saying, hey, this is gamma of p plus 1, and by inserting it into this summation, it's now multiplied by p plus 1. So here's p plus 1, gamma of p plus 1. I know what that's equal to. That's equal to gamma of p plus 2. So if we were to replace both of these by gamma of p plus 2, then this is what it would read now. all of this would be replaced by gamma of p plus 2. And that would be gone, and that would be gone. But look, the term right before p plus 1 is p plus 2. So now I have p plus 2, gamma of p plus 2. That's just equal to gamma of p plus 3. So let's replace the p plus 2 here and the gamma of p plus 2 that I just wrote. Let's replace those by gamma of p plus 3. But wait, right before the p plus 2, there's a p plus 3. So now it's p plus 3, gamma of p plus 3. And the property says that's equal to gamma of p plus 4. Well, you can see this can't go on forever. Eventually, I'm going to be at p plus k, and I'll have gamma of p plus k, which is what this will be replaced by. And then gamma of p plus k times p plus k is going to be gamma of p plus k plus 1. And that's the substitution I can make due to making this substitution. I'm going to make one other one that has nothing to do with the gamma function, and that's the fact that 4 and 2 both share a common root. So 4, I can call that just 2 to the 2k, so it's 2k plus p. So here's my rewriting of this. I'm going to go summation k equals 0 to infinity of negative 1 to the k, x to the k. And then the denominator is going to look a lot cleaner now. We're going to end up with 2 to the 2k plus p, k factorial. And all this junk is now going to be replaced by gamma of p plus k plus 1. And this is called a Bessel function of the first kind, or JP. What happens when p is not limited to being a value where plus p and minus p differ by an integer instead of a non-integer? Well, then we're going to need the Bessel function of the second kind, and we will derive that later this week.